So in the last class we had been discussing how we would use bits to represent text, and we hit on the problem of the zombie apocalypse, where we were using traffic lights on the edge of town to communicate with the nearby towns who could see the traffic lights. And the problem I set for you was to figure out a system of communication using those lights. We had the notes of some guy who was working on this problem, but he met with a terrible end. And so students worked in groups to figure out what was going on there. Most groups eventually figured out that it wasn't 23 times 23 equals 64, but 2 to the power of 3, 2 to the power of 3 equals 64. And each one of the lights could be used like a bit. There was a pair of lights. And so we had 6 lights, which would have given us 2 to the power of 6 equals 64, or, 2 to the power of 8, 2 to the power of 3 times 2 to the power of 3 gives 8 times 8, 64. So we had 64 slots to play with. So most groups, once they figured out that they had 64 slots to play with, the only issue then was to consider what should go into those slots. Okay? So if you take each traffic light to be a sequence of 3 bits, we can organize them like this. And then the only issue is, how do we allocate slots in this scheme? Different groups came up with different schemes, and there are different features. There's no one right way to do it, but in designing a scheme like this, you should consider some of the constraints. So a lot of groups had something like this. I would think, my own view really is that, after the apocalypse, I don't think people will spend too much time worrying about, should that be an uppercase K now or a lowercase k? I think maybe, worrying about case is probably a waste of a resource. There may be, a flourishing genre of post-apocalyptic zombie literature, but, it could probably, not be the end of the, well, I was going to say it wouldn't be the end of the world if you didn't have capital letters, but we're talking about the end of the world. So, okay, now, I think there's a problem here with using that first slot for a letter. I think if both lights being off means A, what happens to the gap between the lights switching? Do you get me? So, like, if you have the word, BET, right? And you signal B, and then very quickly you signal E, and then the lights go off, and then T comes. So you've got BET, or is that BEAT? Now, difference between bet and beat could be, it could be a big deal, depending. So using that space there is risky. Interestingly, you have the same problem in Morse code. If people don't put their spaces in between Morse code letters, you can have confusion. One group, when presented with that problem, used a timing solution. So basically, if you mean A, if all the lights off means the letter A, then they have to be off for a certain length of time. And then it triggers an A. Now, if for some reason you need A, I don't know how you might do that. There's a problem there. But that's certainly a solution. And many communication systems actually use that. They have a clock. And so the transmitter and the receiver maintain a clock. And what they will do is they'll look at the signal at a particular instance. So you might have, every so many nanoseconds. If it's humans, you might say, okay, look, every 3 seconds we'll look at what's there. And provided the transmitter and receiver have their clocks in sync, then if all the lights are off, for 15 seconds, then that might be 4 A's. You look, okay, off, that's an A, off, that's an A. Another problem is they could be all dead. Do you mean they could be all signaling A, 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 A. But actually, they've been wiped out by the zombies. So, I think using that slot is a problem. You can fix it with a clock, and that's what most communication systems do actually. They have a clock. And they synchronize their clocks, and off they go. Okay? I think having a question mark is really useful in a zombie apocalypse. Like, there's a big difference between zombies and zombies. There's a distinction there that could be the difference between life and death. So I think a question mark is a useful thing to have. And you probably also, I think, need some sort of end of message. I remember there was an episode of Scrubs where there was this guy who was locked in. He couldn't communicate. And they figured out that he could blink. And so they would show him letters. And when the letter he wanted came up, he would blink. And so one guy had this big ethical dilemma because the message was, help me to move on. And he spent the whole episode trying to figure out, should he kill this person who wanted to die? When actually the guy's message was, help me to move on my own. He wanted to fight and get better. But your man didn't realize that wasn't he stopped the message too soon. So I do think you need a end of message kind of marker also. And we often have those in communication systems or in file systems. We say, this is the start of the message, this is the end of the message, you can go away now. Missing a space there as well. I think a space could be important. Is this go to get her or go together? Come to get her is very different from come together. Could be something completely different. So you do need a space, I think, and that was missing from a lot of students' solutions. So I think maybe something like this would be best, where you dispense with the uppercase and lowercase. I think that's wasteful. You probably do without that after the apocalypse. Probably leave the lights off. Both lights off means nothing. It's just like the gap between letters. Then you don't even have the timing issue. Like if someone is really slow, you can see the difference between A and A. You don't need a clock for that. You do need a space. I think you do need a question mark. I think numbers would be useful. You might want to give coordinates, lists of how many dead, things like that. Okay. And in some communication systems, in some text systems, you may also have special characters that are shorthand for a whole lot of meaning. So I think in a system like this, if you look at the bottom row there, where all of the lights are on in the left traffic light, and then in the mid and then the right traffic light, we have different lights to mean different things. maybe if all the left lights are on and the green light is on, that could be like zombies attacking from your north. Do you know? So you could maybe see the other town. You can see that the zombies attacking from their north. So you might say, quick guys, zombies attacking from the north, as opposed to like THERE space ARE space SOME space ZOMBIES space TO space YOUR space NORT. It could be all dead by then. So like sometimes we have short codes that mean things. They can be a whole lot of meaning. Okay? So you might have, like a sign for everything's fine here, everything's hunky-dory. You might have like, I don't know, there's a storm coming your way. But you only have 64 slots. And then depending on the context, depending on the system you're using, you should do the best you can with those. So I think most people kind of got the gist of it, but then they were too lazy to redo their grid. I did set you a riddle at the end of class where I said someone has actually figured this out, but they didn't use lights at all. In fact, just quite the contrary. Did anybody stumble upon a system of 6 dots arranged in a grid 3 and 3 to represent text? Braille. So Braille uses a system of 6 raised dots to represent text. And this is probably the first binary system for coding text. So it's interesting to have a look and see how it's done in Braille, because the guy who was designing Braille had the same constraints we had. It's only got 64 slots to play with. How do you code a document in English? How do you encode English text when you've only got 64 slots? As it happens, the problem he faced was how do you represent French in 64 slots. Some people look at Morse code and see there's dots and dashes and think, oh, that's actually the first binary system. But you can't code Morse code in binary because the spaces in Morse code are a whole other thing that you need to code. In Morse code, you have dots, dashes, and spaces. But in Braille, you just have 6 bits per character. What do you do? So you have 6 to the power of 2. No, you don't. You have 2 to the power of 6, isn't it? It's 2 to the power of 6, not 6 to the power of 2. 6 to the power of 2 is 36. It's 2 to the power of 6. Now, it turns out the organization for Braille isn't what you would have ended up with if you were a computer scientist. Okay? First of all, it's our natural inclination to do like 0, 0, 0, then 0, 0, 1, then 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, then 1, 1, 1. Because that's how you'd count from 0 to 8 in binary. In Braille's time, there wasn't any binary math. So he arranged the table quite differently. So to our eyes, it looks a bit, why did he put it there and why did he put it there? Okay, so that's one thing. Also, W doesn't really feature in French. So W was kind of tacked on at the end when people started using it to represent English. So W isn't where you would have expected it to be. But in Braille, we have letters and we have numbers, among other things. And if you look there, well, if we look up at the top first where we have the letters, okay? So in A, it's the top dot on the left, okay? And then B is 2 dots. Now you'll probably find that there is no like nothing on the left traffic light and then top right dot on the right traffic light. Because if you're moving your finger across and you can't see, you're probably just going to come across the 1 dot. So there are some constraints as well. Some combinations wouldn't be very good when you're running your finger across the page to pick up on. Okay? We can see how we look. If you look there at A, B, C, D, E, F, G, H, I, and J, those symbols are used, those combinations are the letters A to J, and they're also the numbers 1 to 0. Now, I'm not sure, but I think maybe in the early days of Braille, you just figured out from the context whether it was a letter or a number. But over time, this number symbol came into use. So this is this here where you have the bottom dot in the left column and then the 3 dots in the right. That came to mean that what comes after me is a number. So if you look here at colon space 2014 space M, you have the C for colon, the 2 dots for C, this one here for O, L is this one here. I've no reason to believe, I've no knowledge that it is. It seems to me that this is a bit of a coincidence that L would actually look like an L. You know, is this a system designed by a sighted person? I'd love to look at the original table and just see, is there logic to L turning up there like that? Or was it just a coincidence? But so this here, this is L. Then I is that pair of dots. And N is this sequence here. Okay? So each black dot there is a raised dot on the page. Space was just space. Okay? There isn't timing involved here, so there's no question of if you're too slow you'll miss the space or what, you know, or the gap between the words. This is the physical space on the page was a space, which is fair enough. Now, this thing here then in red, that's the special symbol that says what comes after me should be interpreted as numbers, not letters. So here we have the number sequence, the number character, whatever. And so then we have B, which can be read as 2. J, is it? Which can be read as 0. A, which can be read as 1. And D, which is interpreted as 4. So by using this special symbol here, Braille was able to, code the numbers for free. He kind of got 2 for the price of 1. Like, he didn't have to use a whole slot, a whole 10 slots for the digits 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. He was able to double up on the meaning of A, B, C, D, E, F, G, H, I, and J. And with the use of just this one slot from his table, he was able to get the numbers kind of for free. Now that's not terribly inconvenient if you're reading it, because the numbers, would come up occasionally. If it was a maths exam, it would wreck your head. If you had 3x by 4y by 72, p dot q times, 3,000, you'd be like, okay, is this a letter now? Is the number? I'm confused. But for regular text, here's a number. That's not such a big deal. Okay, so that was quite efficient because he only had 64 slots. So what do you use them for? If you have 32 uppercase, 32 lowercase, 10 digits, and some punctuation, well, you've blown your budget there. Capitals then are also marked with a special symbol. So that's the dot at the bottom. Presumably it's on the left column, but I suspect a single dot on the bottom of the right column isn't used. I think that could be confusing, but I'm not sure. So here, this is saying that, look, what's coming up is an uppercase letter. It's a capital. So then we have C, O, L, I, N again. With space. These are digits. A, R0, B, whatever, 2, and 4. And then here we have, once again, that dot there says what's coming up here is uppercase. And then we have the sequence for M. So instead of using another 26 slots in the table for the uppercase letters, like 26 for lowercase, 26 for uppercase, we just have 26 slots for the letters. And then if it's uppercase, you get this dot here telling you that. Now, it does make the message a bit longer. Because for these uppercase, like for the uppercase C and the uppercase M, we needed to use 2 characters, or two things, instead of 1. So it does make it longer. It also makes it harder to decode. It needs a bit of intelligence at the transmitter and the receiver. And these are the kinds of things we will see in our modern day communications or representation systems. We see some doubling up. So escape sequences are special symbols in code that don't themselves mean anything. They modify the symbols that are going to come after. So this, dot and then 3 dots on the right, that doesn't mean anything. It just says, well, what comes after me is a number. This dot doesn't mean anything by itself, but it says what comes after me is an uppercase letter. We see escape sequences a lot in computer systems. And they can be used to extend the system to represent things that the number of bits wouldn't otherwise allow. So you have these special sequences that do, some voodoo that can allow things to double up. So another system which you could use to send messages over distances if your mobile phone isn't working anymore because the zombies got to that, is Semaphore. So Semaphore has been around for a very long time, and it's used for communicating across distances. So you would have had people on mountain tops, or you would even have had machines. You used to have like kind of things that looked almost like windmills, and they would have arms that would go up and down, and they could send messages, across great distances. And that's what people used to transmit messages over long distances before we had the telegraph. You typically see it today between ships. And of course it's only good for daylight. It doesn't work at night. But ships used to use it to communicate with each other. So you can imagine, the Battle of Trafalgar or whatever. It's not like, 300 ships from each side headed off and we said, right lads, no, just, attack the bejesus out of them. Like, there had to be coordination and organization. You would have had special symbols for retreat, special symbols for whatever. Here, with Semaphore, we have a combination of flags to represent letters. If you look there, how many positions can a flag have, right? Like, let's say I've got my arm here. There's what? There's 1, well, up here, isn't it? That's as high as it goes. 1, 2, and is it 3? How high? How many ways could my right arm go? Oh no, you can go straight up. Look, you can have straight up, 2, straight out, 3, 4, and you can be straight down as well, so 5. So if you had one arm here with 5 positions, another arm here 5 positions, how many possible things have you got in your toolbox? Got 5 by 5 is 25. That doesn't really work. You know, we've got 26 letters. Whatever about, you know, our numbers and our uppercase and our, you know, zombies attacking by boat from your left. I mean, we can't even do our letters with 25. So actually, that's why you have to actually have hands crossing over. If you look there on Z, this left arm here, or whatever, this one anyway, this crosses over, giving it another position. So this hand can be 1, 2, 3, 4, 5, and then over here. Similarly for, I think, O there, it's 2 in the same, whatever. I'm doing the math right now, but 2 in the same side. Okay? And you'd have to, because if you only got 5 and 5, you're not going anywhere. Okay? So we have hands to cross over, so we can have more combinations. Okay? We don't do uppercase and lowercase. Right? You're not going to transmit a novel or poetry, you know, on the high seas. It's for short messages. So we've got what? How many positions? Something like, not many, I mean something more than 25, but not a whole lot more than 25. You could count them up there. We double up then letters and numbers. So just as Braille duplicated the symbols for A to J, for 1 to 0, in Semaphore, if you just saw a picture, a single still picture of a guy holding 2 flags, you couldn't tell whether he was talking about a number or a letter. You would have to have seen the whole thing and have some memory of whether you're like in numbers mode or letters mode. So there's a special symbol there where he's like, step into the map, Joey, like that. That's saying what's coming after me is numbers. And then this one, all right, which is just one arm down. Okay, that makes sense. This is numbers, going back to letters now, going back to numbers now, letters now. Okay, makes sense. This is numbers. Sorry, we're going back to letters. So this says whatever's coming after me is numbers. This is saying whatever's coming after me, we're going back to letters now. And numbers are a big deal at sea. You know, if you're going to say change course to, you know, heading whatever, like numbers do feature much more in messages at sea than they would in regular text documents in Braille, for example. Okay? So, let's look here at colon space 2014 space M. Right? No uppercase, lowercase. Not important at sea. So here we have C, O, L, I, N. Interestingly, I'm not sure what would happen if Colin had 2 L's. If it was C-O-L-L-I-N. Like, does he kind of do a little wave, or I don't know. But do you know what I mean? How would you like? Or is there timing? You know, do people who do this? Is it like, you know, dum 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 dum? Like he knows what he's doing, and the timing tells you. I'm not sure what C-O-L-L-I-N would look like. Space or rest is just 2 flags down, which if you think about it is good. If you're a bit tired and you need a rest, you know, interpreting that being misinterpreted as lots of spaces, that's a good thing. Okay? This one here then is special. This is the one that says what's coming after me is numbers. And so this one here is the letter B, or the number 2. Now we're in numbers mode, so it's the number 2 as opposed to the letter B. But if you just saw a picture, you couldn't know whether it was 2 or B. You had to know what came before. So already, if you think about it in computer processing terms, the receiver has to have a memory. It has to have some storage to know, am I in, numbers mode or letters mode. The next symbol here is for the letter K, or the digit 0. The next one here is for the letter A, or the digit 1. And the next one here is for the letter D. I had to look, you can kind of figure that out, A, B, C, D, or the digit 4. Interestingly, this is a lot in common with Braille. But if you're stuck, if you've only got so many slots, that's probably what you'd kind of have to do, It makes sense. I do find it interesting that both Braille and the people who, when Semaphore evolved, they went 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, A, B, C, D, E, F, G, H, I, J. I think someone, if I got you to design a Semaphore system today, you'd have probably gone 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But anyway. But of course, putting the 0 at the end allows someone to go, A, B, C, D, E. Okay, send E for 5. It's not as natural as to go air, 0, 1, 2, 3, 4, so maybe that's it. Maybe it helps, count these things on your fingers. Although I can't imagine those guys on ships, Okay. So then we have a rest again. And then this is saying, this is the symbol for J. Now we were in numbers mode. There is no number corresponding to J. So this is saying, okay, well, then we've gone back to letters. So now we're in letters mode, so to speak, and the next semaphore then is interpreted as an M. Now, as it happens, it could only be interpreted as M. There's no corresponding number to go with M. But you do need a system like that, because if it was Colin 2014 H and you didn't have a special switchback to letters sequence, then you wouldn't know whether you're talking about the letter H or the number 8. Now, God forbid there is a zombie apocalypse. You now have 2 ways to communicate with the town down the road. But that's not why we looked at these things. What's interesting is that these systems predate even the beginnings, even the first hint of our computer systems and the first hint of our telecommunication systems. But they have in them some of the features that we see, because they were faced with the same problem. You've only got so many combinations, only so many ways to represent things. There are only so many different possible slots we can use. How do you efficiently use what you've got? And you have to look at the scenario, you have to look at the context. A person on a boat bopping around in the sea is a different context as well from a blind person, sitting in a room. which is different again from a zombie apocalypse. And you have to adapt and figure out what you're, what's the best way to go. Okay? So I think we'll leave it there, and I'll see you the next day.